eigenvalues of the observer dynamics. Where should we place the poles of the observer dynamics? Let's say you have a system where the system has open loop dynamics. The open loop eigenvalues are here. Let's say you have a system x dot equals ax plus bu, and the open loop dynamics has eigenvalues here. Okay, let's say that. Let's say you design a controller, a minus bk times x plus br, such that the closed loop eigenvalues have moved from here to here. Okay? This is just something I made up. Let's say this is the open loop dynamics, open loop eigenvalues of a system. This is just an example now. Okay? And let's say this is here closed loop dynamics, closed loop. So this is nice. The system was unstable. Now the system is stable with my feedback gain, this one here. Okay? It's quite nice. Now everything is good. Question is, where should I put the eigenvalues of the error dynamics in this picture? First of all, I know it shouldn't be here, right? If it's on this side, then this will become unstable. The error will grow to infinity, which means x minus x hat will go to infinity, which is not something we like to do. But it should be on this side. So I give you a few options and you tell me if it's okay or not. For instance, let me put it here. Say this is number 1. Another thing is, let me put it here. Okay. Another one, let me put it here. Another one, let me put it here. Which one do you like the best and why? I guess a lot of you would probably vote for this one. For this one? Okay, some people vote for this, some people vote for that. What's the problem with this? There's a large oscillation, you don't want oscillation, so that's not good. Okay. But what's the problem with this? So what?
It takes a long time to converge.
Yeah, it takes longer time to converge, but eventually it will converge. I mean, is this something you could use at all? You don't want to use it. You don't want to use this, that's right, but there's another reason for it other than being slow. It is behind the closed loop system, which means who will converge first, the closed loop system or the observer? The closed loop system will. Can the closed loop system converge with wrong estimates of x hat? No, that's the problem. You see, I'm feeding x hat now into k. You see? So, and I'm expecting this to converge, the closed loop to converge faster than this. But it can't because it's feeding the wrong x hats. So how can this part converge with wrong x hats? I need the correct x hats first and then expect this to converge. Do you understand that part? So therefore, the convergence of the observer must be faster than the closed loop if you want the closed loop to converge in a certain time. Okay? So that's a trick. If the requirement of the closed loop is to converge at a certain speed, okay, then the observer must converge before that so that this can in fact converge at a certain time. Because otherwise you will have a system, a closed loop system that wants to converge but can't converge because the x hats are feeding back not correctly. So if the x hats are still changing because of the error in the observer, there's no way that this can converge in time. Understand? So therefore, you want the observer dynamics to be faster than the closed loop dynamics. Yes?
Why didn't you use our pulse onto real axis to cancel oscillations?
I'm sorry? You put it on the real axis?
Yeah.
Yes, you can, of course, but since I chose two of them, like this, like two conjugate pairs, sometimes they cannot be exactly, the imaginary parts cannot be exactly cancelled to zero. So I always find it safer to say they are very close to the real axis. So I'm bringing these guys closer to the real axis as close as possible. Sometimes it's not possible to make them exactly zero. That's why. Okay? Because then they will be on top of each other. If they're exactly zero, they will be on top of each other. And there are reasons why they cannot be sometimes on top of each other. But they will be very close. That's why I do this. Okay? Any other question? Okay. So let me take this as a note here then. Where should I write this? We desire, let me write it down here. We desire that the aerodynamics is faster than the closed loop dynamics. And I just explained to you why. I hope you understood. Right? Yes?
How did we eliminate the last one?
This one?
Yeah.
I didn't really eliminate this. It can be this one or this one. In fact, it could be this one as well. It's just that there's oscillation here. Okay? And yes, you're right. You would prefer this one. But this would still be working. You would just see in the transient, you would see more oscillations in your output. Because look, if you have oscillations here, listen. If you have oscillations here, you're looking? Okay, if you have oscillations here, you would have oscillations here. I mean, in the aerodynamics will have oscillations. If you have oscillations here, you will have oscillations in the aerodynamics. Which means the real x, let's say this is time and this is x. And x is doing this. Okay? So oscillations in the aerodynamics would be something like that, if this is x hat. So x minus x hat is this distance. You see? So this would be, the red one would be x hat, and the real one would be the blue one. So eventually, as time goes by, if this dynamics is correct, eventually they will match. But at the beginning, you will have these oscillations. And the oscillation is in the aerodynamics. You see? So what's going to happen if you're feeding back x hat into the system? The system will think that you're oscillating. Right? Your controller will think you're oscillating, because if the system was really oscillating in real life, then you could have this one, and this one would tell you, oh, I'm oscillating, so it would do something over here. It would probably also give some oscillatory input to cancel it out. But in reality, this guy is not oscillating at all. What's oscillating is the observer. Right? So you will have this oscillating signal into K, and then it would generate some oscillating U over here, and that would indeed be oscillating X. Until when? Until these two are matched. Then you will generate the right U's and so on and so forth. So if you had an oscillating observer, it would in fact oscillate the system, because you would have an oscillating input over here, because you would think that you're oscillating. In fact, what you're oscillating is not real. I mean, the aircraft is not oscillating, you just think you're oscillating. You don't really want an oscillating observer. So what's going to happen? Well, you're first going to oscillate for a while, and then you will match this one, and after that you will converge to your steady state, whatever. That requirement in the closed loop, though, says to finish that oscillation or come to a steady state in a certain time, right? Because of this open loop requirement. So you might be oscillating at the beginning, but you will reach that point eventually anyway. So what I'm trying to say is that an oscillating observer, X and T, and let's say this is your steady state. In this case, it's 0 because it's a linear model. Let's say with a good observer, you might be doing this, and you are in steady state somewhere over here. Okay? With a bad observer, you might be doing this. They converge both about the same time because the eigenvalues of the closed loop are at the same place, and the eigenvalues of the observer dynamics is faster anyway. So the error of x hat will die ahead of time anyway. So at the end, the closed loop will all match at the same point. Okay? So even if you do have oscillations over here, you will probably see it in the transient, but not at the end. So if the requirement is to take the airplane and settle it as fast as possible, or not as fast as possible, in a certain eigenvalue in a closed loop system, you could still achieve it with this. But if you have more oscillations than this guy, then you will see a lot of oscillations. So typically, of course, you don't want that. You want less oscillations so that you match that thing. So you would need an observer that is somewhere here and that's faster than the open loop, the closed loop. Can you have it really far away? That's another question. Can we have it really far away? Somewhere here. Can we have the eigenvalues really far away? All the way. Why not have it 10 million? Right? Why not have it at minus 10 million? This is at minus 0.5, and this is at minus 10 million. What's the problem? It would be great. It would go to 0 in a heartbeat, the error. Why can't we do that in real life? Why? Why not make it 1 million? If I make this 1 million, probably this k will be equal to 1 million, and it would be great. You see an error multiplied with million, go down here, and in a heartbeat you are back to 0. Why doesn't that work?
Maybe you can farm the airplane.
How and why? Well,
Strict movement.
no, but the strict movement is not in the airplane, it's in the error. The error will go, the error here will go immediately, like boom, it will immediately match this.
If the error is oscillatory,
Yeah.
it will oscillate forever.
Yeah.
And then it goes
So
up.
we want to have the large undershoot, overshoot, and all this. So here's what you need to be careful here. See, if you're looking at the error between y and y hat, that assumes that the measurement of y is perfect. What if the measurement itself is wrong? Understand? Have you ever measured anything in the lab? I hope you did so far. Was it always perfect? It was never perfect. So this is always, you always question this. So if you have a measurement error, okay, so if the measurement is y plus some measurement error, let's call it like this, then you're multiplying this error also with this k, which will cause all sorts of problems inside, right? Because you're multiplying not only the measurement itself, the real value, but you're also multiplying the error with it. So you take this error and multiply it and send it into the system. So a lot of things will happen there as well. So you don't want that. Okay? And where do you send it? You send it in this thing, and you take the integral, and you're taking the integral of that large error on top of everything. You see that, right? So you're doing this 60 times a second. 60 times a second, you're taking this e, multiplied with a large number, and take the integral on top. So that will be fun. Okay? So we don't do that. So therefore, we are always a little bit conservative and say, well, we want to be a little bit faster than this, not really too fast, but make it somewhere meaningful. Okay? And this is what a designer should be doing. When you design an observer, these are the things that you need to consider. Okay? And therefore, there's not really a cookbook for these things. A cookbook, you know, a cookbook, you take a cookbook when you want to cook. It says, 2 eggs, do this, and then a little bit of water, a little bit of milk, then do that, and then you have an oven of 400, and then wait 20 seconds, comes out, never tastes like your mom's. Right? So because there's always something that you miss in the cookbook. Okay? And this is pretty much the same thing. I'm telling you this as if it was a cookbook, but there's always something that is specific to the problem and that makes the distinction between a good aerospace engineer and not so good aerospace engineer. To understand, to make these kind of decisions, you need to understand the theoretical part, but you also need to understand flight dynamics. Because if you don't do flight dynamics, you can't make these decisions smartly. Understood? Okay. That's why we sometimes call this flight mechanics and control. A lot of groups are calling themselves flight mechanics and controls because they go hand in hand. Okay? So, any questions so far? All right, so how do I calculate KE? There are lots of ways to do that. Of course, we can assume an A prime, saying that, okay, let's assume an A prime, let's assume a desired A matrix, and then make this one equal to that, and then make some manipulations and calculate KE. Of course, you can do that, right? That's quite straightforward. We can simply say A prime is equal to A minus KE times C, and choose KE such that these two match. Of course, we can do that, all right? But of course, if C is invertible, the system becomes a lot simpler, right? You can do A prime minus A is equal to KE times C, like that. And then you invert C, and then you find KE uniquely if C is invertible. That means C is a square matrix. But this is not always the case, of course. All right? So another way is actually to use Bascura formulation. There's a dual thing for Bascura. Let me do it here. If you know the eigenvalues of the desired A matrix. If you know the eigenvalue of that, then you could use one way of the Bascura formulation, and KE in this case is alpha minus A. Again, the same thing. And observer gain inverse of the observer matrix, and this is the observability matrix. And you see, you can do this if the observability matrix is a function of A and C. If the observability matrix is full rank. Full rank, which means it is invertible. Right? Again, this is for a single input system, by the way. Okay? I'm not telling you that Bhaskara is the only way to find this. This is just one way. And, you know, I barely use this myself. I would rather choose an A matrix that I like, and I would try to find KE based on that A matrix. Okay, that's what I would do. But still, I want you to see that there's a duality between the controls problem and the observer problem. Just based on the fact that the closed loop system looks like this, A minus BK times X. And you see the duality. Duality is not the right word because duality has a different meaning, but you need this, you see how similar they are, the problems. Okay? Here you're trying to find the K such that to match a certain closed loop system. Here you try to find K to match the aerodynamics the way you want. Is that good? Any questions? Gonna do an example now. Is that okay? I think I've said everything. Oh, there's one more thing. I forgot. All right, good. When does this error happen in first place? If there is an error, this is going to happen. If there's an error, that's going to happen. Yes, if there's an error, all these things are good. If the error starts somewhere here, how fast will the error go down? Okay, so we established that. But how does the error happen in first place? Look at the system. You have A, you have A, you have B, you have B, you have C, C. I mean, if you do this in the computer, you won't see an error because you're doing the same calculation here as here. So where does the error come from? Do you understand my problem? I have A, B, C. I have A, B, C. So if you do this in the computer, you start the simulation, believe me, you will see zero error at all times because A, B, C is exactly the same. The error will come from all the dynamics that is not represented over here. Because in real life, this is only valid at the equilibrium point. So in real life, when the airplane just moves away from the equilibrium point, suddenly these ABCs don't match anymore. And then you will have an error. Okay? Another thing is you might have an error over here in your measurement. You might not measure it perfectly. Another error, source of error might be this one, this U. U comes in here, maybe that requires also measurement. Maybe there's an error in that measurement too. So there are lots of sources where this doesn't match that. Okay? When I canceled these two, nobody said, hey, how come these B's are exactly the same? Right? Because this B belongs to the aircraft, and this belongs to the observer. Imagine in real life I choose a B and the airplane is flying around. Of course the B keeps changing, right? So then your observer is really valid around that equilibrium point when you're not too far away. If the airplane is another altitude, another speed, you probably need another observer. And then another observer means that you need to keep the same architecture, but you keep changing K, just like you keep changing K on the controller. This is what we call gain scheduling. Schedule means, as a function of time, you're changing things. So when you go to a certain altitude, you go to a certain speed, you choose a certain K. Same way, at that certain altitude and a certain speed, you choose a certain K over here. So how do you go from one K to the other? Well, you can have a hysteresis, right? Or you can you can average it out and go slowly from one to the other. Or if you're too lazy, you just go one to the other. You just choose that, and then you choose the other one. But in between, you might have some problems because of the discrete jump. Okay? I mean, this is how we do it in practice. Let me not confuse you too much with this. But you need to understand that this observer dynamics is really valid only at this equilibrium point again. Okay? So if you're a little bit away from the equilibrium point, then this will not match this one anymore. Okay? And another thing is you might not be having the perfect measurements. So in other words, the aerodynamics doesn't really look like that all the time. It always has some input to the aerodynamics. And this is like an input to the aerodynamics. So if this is equal to 0, okay, everything is perfect, aerodynamics will go to 0. If there's some input, this one will still try to bring it back to 0. But if you have persistent inputs over here, then the error will always persist on the other side as well. Okay? And where does this delta input come from? Well, it comes from all these wrong measurements and estimations and so on and so forth. And note that this delta is very similar to B times R. An input to the aircraft, and here is your system dynamics. This is an input to the aerodynamics with your system dynamics in between. So the problems are very similar. Understood? Any questions? Yes?
For the same equilibrium point, isn't that B and the other B is the same?
Yeah, at the equilibrium point, yes.
For the same equilibrium point, we can say that both A and B's are the same.
Yes, and therefore there's no error. Maybe you don't really need an observer. If you know if these B's and A's are the same at the equilibrium point, and they are, then the observer will see 0 error, and you will have perfect x hat coming from here. The problem is, first, they are not. I'm sorry, you're not always at the equilibrium point. Second problem, it's actually a much more important problem, is that how do you find ABC in real life of an aircraft? Let's say I give you an airplane, okay? And I tell you, find the ABC matrix. How do you find that? Experiment. You do experiments again. You go to the wind tunnel, you do the aerodynamic derivatives, and how good are these tests anyway in the wind tunnel? Are they perfect? No. So you will never find the exact ABC matrix. There will always be some errors. Sometimes the errors are small, but they can be very large as well. And you think you have the ABC matrix of your airplane, but in fact you don't. Okay. You can do CFDs, you can do wind tunnel tests, you can do all sorts of things. Remember, in flight mechanics, we find the AB matrices through what? Through aerodynamic derivatives. Where did they come from? Well, you find CL alphas, you find CM alphas, betas, and all that stuff. Where do they come from? Well, you measure them in the wind tunnel, you do CFDs. And this is where all the technology really is, to find these things perfectly. If you don't find them perfectly, in other words, if you find them perfectly, then these will become much better in real life. If they are not perfect, so the CFD people, they just give you some numbers, and you do this, and you assume that your aircraft will perform perfectly. And after all this work, you realize your controller is actually making the airplane unstable. What do you say? Right? You will say, oh, my airplane is now unstable. Did I do the controller wrong? And you calculate. No, I did it right. Then maybe the ABC matrices were wrong. And then you go back to the CFD people and say, my ABC matrices are not correct. Do your CFDs again. And they will say, no, mine are perfect. I think you are doing it wrong. And that's where you need good communication between engineers. Understood? I sometimes say engineering requires a lot of capabilities. A good engineer requires a lot of capabilities. One of them is definitely communication. You need to communicate well with your partner because you can't do everything by yourself. Okay? Any questions? All right, let's do an example. Right. Example. Recall, I keep doing the same example, but it's good because we have a base and we can compare things. Recall the example, the previous example. Right. And we had something like this. I is equal to 1, 0, x. So the output is really y is equal to x1, right? That's the output. But for full state feedback, we need x, x1 and x2. And according to this, x2 needs an observer. Needs an observer. Because x2 is not measured in this system. Okay? x2 needs an observer. In the previous problems, I did it very simply. I said, well, x1 and x2, let's assume they are measured. Let's design a controller that uses x1 and x2. Right? Now I'm saying, well, I have a measurement for x1 and x2 is not measured. So you design an observer for x2. Okay? The desired characteristic equation of the controller, the full state feedback controller, the full state, or let me write this as a question. Design a full state feedback controller, full state feedback controller. Design a full state feedback controller such that I think that was the problem. Seven. So therefore the desired characteristic equation was like this. That is the desired characteristic equation, and this had eigenvalues at 17 minus 68 plus minus 17.66 I. Okay, these were the desired characteristic equation and the roots of the roots of the closed loop. Roots of the closed loop. Of closed loop. And we have designed a feedback gain for this. I think it was something like 16 and 9 or something, as I remember. So we designed that. So our goal is to design an observer. Design an observer to estimate x. Okay. So the first question is, of course, what do we do? If you design an observer, what should we look at first? Is the LTI system, linear time invariant system, observable? Because if it's not observable, none of these things will apply, right? We can't observe. if it's not observable, which means some of the x's we can't even see based on looking at y, we can't see them. So looking at y and u, we can't estimate x. That's what it means, right? If it's not observable. So how do we check observability? We look at the observability matrix, which is a function of A and C, right? And because if it's a second order system, it will be C, CA, right? So C is equal to 1, 0. Is that right? Yeah, it's 1, 0. And A times C will be minus 3 and 8. Okay? So look at the determinant of this. And that will be equal to will be 8. Therefore, it is 4th rank, and therefore it is observable. The LTI system is observable. So that's good. Is that clear? All right. Second question is, where should be the eigenvalues of the observer error dynamics? And you make a decision while we are going on a break. And whatever it is, I'm going to use it. Okay? Yeah.
For the observability dynamics, we have 2 modes and 4 eigenvalues.
Which one? Yeah.
Should we choose 1 KE or 2 KE?
A KE is a vector or a matrix or a number, depending on what we have over here. What was your question? I didn't get it.
We have voice mode and short to read, right?
Yeah, in that case, we have 4 eigenvalues.
Where should we have 1 KE or 2 KE?
Well, it depends what your measurement is. Let's say we have 4 modes, and how many measurements do I have? What do I measure? 2 of them? 2 of the states or 4 of the states? If I measure only 2 of the states, then 2 will be my input over here, right? And what is my outputs? How many controls do I have? 1 control, then 2 coming from here, 1 signal coming from here. So this should be a matrix or a vector or a number. 2 outputs, 1 input. What should we be this? 2, 1. Should be a vector. In that case, then this KE is a vector. Okay? If you have more inputs over here, more outputs over here, then it should be a matrix. If you have 1 input and 1 output, it should be a number. Everything we do here, there are either vectors or matrices or numbers, scalars. Okay? But we don't restrict ourselves to scalars anywhere. Answered? Okay. Any other questions? All right, let's give a break.